En principio sí. Sí.
We're going to start. Today we have a master thesis defense by Adrián Nadal Rosa, and this has been supervised by Gonzalo Manzano. And I think that you have 30 minutes for your presentation, and after that we will make some questions. Okay, you can start.
Okay, so good morning, everyone. So again, here today to tell you our master thesis based on a thermodynamic description of the fluctuations in the rotary molecular motor F1-ATPase. The idea is obtaining one description that allows us to obtain hidden information about the system that is otherwise inaccessible. I will first present the importance of molecular motors in general and the F1-ATPase in particular, followed by some basic ideas in stochastic thermodynamics, the theoretical framework in which I work, and then I will just continue with the typical structure for this presentation about methods, model, results, and conclusions. So, molecular motors are basically machines that take as an input of energy the one that comes from the hydrolysis of ATP molecules and transform part of it into mechanical work that is used to display whichever function the cell needs to be done. This can be the rotation, the movement of the flagella in bacteria to allow the locomotion, every steps in the protein synthesis process, vesicle transport inside the cell, but again, they are in charge of almost every single process inside the cell. So if one wants to make a proper description of the dynamics at the cell level, one cannot lose sight of these molecular motors. And in particular, one cannot lose sight of the F1-ATPase, because this is the one in charge of synthesizing all the ATP molecules that will be used for the remaining molecular motors to perform their tasks. It works as follows. The rotary molecular motor is part of the ATP synthase complex, which is also composed by a F0 domain, which is empty in the cellular membrane. When a proton flux gets across the F0 domain, a rotation is induced in the gamma shaft of the rotary motor, enhancing the hexameric ring of alpha and beta proteins, allowing for all the conformational changes needed to basically take ADP and inorganic phosphate from the media and then synthesize the ATP. Now, remarkably, this motor can work in reverse, taking ATP molecules and obtaining the energy stored in the bonds by breaking it in an hydrolysis process. But take into account that whenever the cell needs to store energy, it needs that the system does this efficiently. This is that it rotates predominantly in the synthesis direction. And when it needs to take all the energy stored in the ATP molecules, it needs to make it rotate in the hydrolysis direction. So you always need of unbalanced transitions. You need to work out of equilibrium. And it's at that point in which we introduce stochastic thermodynamics that has been greatly used in the last decades to model these sort of systems. In its simplest form, we could say that stochastic thermodynamics is basically a thermodynamic description of an intermediate set of scales between the microscopic and the macroscopic world in which the thermal fluctuations are still important. But instead of trying to make a non-equilibrium description from a microscopic perspective, which introduces a lot of difficulties, one makes a description of this mesoscopic intermediate regime from a point of view of the macroscopic realm. This is identifying some energy fluxes and irreversibility. Let's first to settle this mesoscopic regime, beginning with as a starting point with an equilibrium closed system at a closed temperature. What we need to characterize this mesoscopic regime is basically making some coarse graining over the microscopic configurations that you have. If you're in a closed system at a fixed temperature, once you assign a Hamiltonian energy for each of your microscopic configurations, you can obtain the probability of observing each of these microscopic configurations by using the canonical distribution. Once you have these probabilities, you know that the probability of observing a particular mesostate in which some microstates are coarse-grained is basically the sum of the probability of seeing all of these possible microscopic configurations coarse-grained in the mesostate. That's what is done in this equation, in which the free energy of the mesostate is basically defined as the free energy of the state, but restricting the sum only over those microscopic configurations that are coarse-grained in it. Once you have the free energy, you can obtain all the remaining thermodynamic potentials, internal energy, entropy, whatever you want, and hence having a full description of these mesoscopic scales in this equilibrium setup. But as I said, we're interested in non-equilibrium behavior. So we need to ask also about the time evolution that these probabilities of observing the mesostates will show. If the mesoscopic description is done in such a way that the microscopic dynamics inside each mesostate is much faster than the mesoscopic transitions at the mesoscopic level, then you can say that the mesoscopic dynamics is memoryless. And then you can propose for the time evolution a master equation. Now, this is in general an equation that you can use for continuous in time, discrete in type space, Markovian dynamics. But as I said at the beginning, what you want to do is to make a thermodynamic description on these fluctuations. So at this point, one needs to wonder about what constraints does that imply on the equations you want to propose for the time evolution of your system. In particular, the only one that you a priori can impose is that if these distributions were the equilibrium distributions we were showing right now, all probability fluxes must cancel out. You must ensure that all transitions are balanced. What allows you to write a constraint on the ratio of rates, which is the so-called local detail balance. Now, the idea is that we want to adapt this result to non-equilibrium setups, as I said. In molecular motors, in the literature, what is usually done is identifying the molecular motor itself as a core system and then coupling it to different equilibrium reservoirs, in general, particle and work reservoirs, such that to adapt the free energy inside the exponential as this local detail balance condition, you need to split the now non-equilibrium free energy into that coming of the core system itself, which will be our molecular motor, and that of the reservoirs. That coming from the exchange of particles with the particle reservoirs, and that of work reservoirs that are modeled in general by saying that they introduce a general input of energy delta x prime in a transition from x to x prime. This is, as I said, the information you can impose a priori about on the master equation for this thermodynamic description, which is actually only our constraint on the ratio of these rates, but gives you a lot of freedom to define the rates themselves. One possibility is always to basically put some factor in which you could encode all different details, for instance, all possible dependence you want to include with external parameters that will cancel out once you do the ratio, and then simply have the argument of the exponential. This is the proposal we used, although, as I said, there's some freedom here. Now, since we're working in non-equilibrium setups, probability fluxes in the master equation are not zero anymore. That means that at the end, the state of the system will be randomly changing and hence will be describing an stochastic trajectory, which is actually what you will be measuring in experiments. So stochastic thermodynamics, what tries to do is make this description of fluctuations from the macroscopic point of view with energy fluxes and reversibility, focusing on these experimental measurements, focusing on a description at a trajectory level. There is, for instance, I don't have much time to talk about this, but what happens with the first law, which is defined at the trajectory level, basically saying that the total energy change in a trajectory, this is the final energy minus the initial energy you have, can be identified as the contribution of two general fluxes, one in which you simply encode all the possible contributions of external forces that you name work, and another one that accounts for the interaction with thermal reservoirs, which is the heat. Similarly, one can recover the second law of macroscopic thermodynamics by first identifying, as is done in the macroscopic regime, some term in the total entropy change of the system intrinsically related to the reversibility of the process. That here we can see as this stochastic entropy production at the trajectory level that compares the probability of seeing a forward process and its rewinding one, the time reverse one. If you take the mean value of this stochastic variable, you see, once identifying the Kullback-Leibler divergence, that it must, on average, always increase, which is what gives you these ideas of macroscopic thermodynamics. But again, I want to say that we're working with a stochastic variable. So if you want to properly describe the evolution of the system, you need then to identify, to be able to characterize as much as you can the probability distributions of all these stochastic variables. So you can use all the techniques that probability theory can give you to describe them. In particular, in stochastic thermodynamics, in the recent years, martingale theory has begun to be explored, mainly from the fact that some thermodynamic potentials, as this exponential of the entropy production, have been identified as martingale processes. Once you see this in your systems, then you can use all the previous results that are used to characterize the statistics of martingale processes to characterize the statistics of these functions of your thermodynamic potentials, and at the end of your thermodynamic potentials themselves. In particular, in this work, I focus on two main results. One, which is the integral fluctuation theorem at stopping times. That is basically a constraint that you can impose over the mean value of this function of the entropy production, and bounds to the extreme statistics of the entropy production. The main idea in this context of thermodynamic inference is taking these two general results and writing down some closed expressions for parameters that are otherwise inaccessible to measure or difficult to be measured directly in an experiment. So let's see in what system I apply these results. But first I want to mention one word that actually serves as, let's say, motivation for the particular problem that at the end we propose for the master thesis. What we proposed is obtaining, so being able to infer from the fluctuations of the system a potential external agent that could be biasing the motor to rotate in one of the two directions. This external force comes from this reference. One of the original ones in which thermodynamic inference was used not only to obtain bounds to certain parameters, but to accurately obtain one bound that was otherwise inaccessible, or, well, in this case, just diffuse, which was the intrinsic torque that the motor does against an external environment when it is rotating. Basically, they could characterize with results of stochastic thermodynamics, which is the detailed fluctuation theorem, which was the probability of making an angular displacement in one direction and the same angular displacement in the other one, so that they could simply see directly the motion of the motor, see how it rotated, the simple movement, and characterize the work it was exerting against the external force. So this was, as I said, the motivation for including this potential external agent biasing the system. So, based mainly on the main features that were described in the seminal papers of the 90s about the behavior of the motor, we proposed a very simple model with only 3 states, in which the motor can be empty with the ATP molecule bound, which this is the fuel it needs to perform the task, and with the ADP or with an ADP bound. This is after you make the hydrolysis, what you get as a product of the reaction in your motor. The only observable pair of transitions are those that involve a movement of the motor, which in this case are hydrolysis and synthesis transitions that involve discrete 120-degree step. It's in this transition in which we will include this external force. Now, identify the model to properly obtain an expression from the rates of its transition. We need to write down local detailed balance, and for that we need to identify which are the reservoirs to which we are coupling the different transitions. We basically couple all pairs of transitions to a thermal reservoir which is at the same temperature in all cases. And when an exchange of particles is involved, we put the corresponding particle reservoir, either an ATP particle reservoir or an ATP one. And we include, as I said, this external potential factor in the reservoirs that are coupled to the synthesis and hydrolysis transitions. One can simply put all these drivings into local detail balance, and then using this proposal I showed you at the beginning, write down the rates for all pairs of transitions. Now, that said, I go into the point that what you're going to be measuring in an experiment are a stochastic realization of the system. So what you want to do in your simulations is precisely obtaining this sort of simulated stochastic trajectory that one could measure. And for that, we simply use the Gillespie algorithm. We basically need from some initial state at a particular time to construct a set of states that are visited at some instance. So for that, we basically use the algorithm that has 2 main steps that are repeated consecutively, which is obtaining from this probability density function the time of the next jump, taking into account all possibilities that could have. And then once the jump has happened, you use the conditional probabilities to decide which particular jump at the end you're doing. Okay, that's it. Let's focus on what I have done in particular. So let me begin talking about the results with the integral fluctuation theory. At the end, as I said, this is a theoretical result that you can take as some constraint on the statistics of your thermodynamic functionals. So from which you want to obtain a closed expression for the parameter you want to infer. So in our case, what we did is to define a stopping protocol that allows us to know exactly the entropy produced at the stopping condition. And that this entropy production depends on the parameter you want to infer, for sure. And to do that, you must take into account that the only thing that you will be able to measure in a real experiment is the movement of the motor. The only information you have is that it moves 120 degrees step in an hydrolysis to one direction, in the synthesis to the other. Besides, one must know that this angular displacement of the motor needs of consecutive cycles in each of those directions. And that the entropy production in those cycles has the parameter we want to infer inside. So what we did was to propose a stopping protocol based on the angular displacement of the motor at a particular time, in which the motion of the motor was ceased whenever it reached a concrete angular position in the hydrolysis direction or in the synthesis direction. And since you need to fully know which is the entropy produced in the stopping conditions, you also need to ensure you know the initial state of the system. And that's why we begin the simulations after the first hydrolysis is detected. Because in that case, you know that you're ending up in the ATP bound state, and hence you can begin to count cycles turning back to this state whenever you see consecutive transitions. I have not much time to explain how to obtain it, but the entropy production at these boundaries can be easily obtained. Mainly, you can see this term that accounts for this entropy production I was telling you produced in a cycle times the number of cycles you're imposing, plus some change in the surprise-Salor and others. But most importantly, these two expressions does neither depend on the specific trajectory nor on the time at which the stopping protocol is met. They only depend on the boundary that you have reached to stop the motor. That allows us to go back to the integral fluctuation theorem and basically write down an equation saying that the mean value is the exponential of minus the entropy production at one of the boundaries times the probability of reaching that boundary. That's the same for the other one. Since the motor is only stopped because reaching one of the two boundaries, the sum of the probabilities of reaching one of the two boundaries that the motor stops because whatever reason, because of them both, must sum 1. So plugging into this final expression the previous results for the entropy produced at the stopping condition, one can obtain a closed equation to solve for the external world. That need of two experimental measurements. One, the probability that you end up because reaching one particular boundary. In our case, we wrote it for checking the probability that you end up because reaching first the boundary in the hydrolysis direction. And this other gamma parameter, which is actually a measure of the irreversibility of the process that, loosely speaking, is basically a parameter that is measuring how much information you're losing, how much trajectories you're not taking into account, because imposing some stopping protocol that fixes, for instance, the initial state. The problem with this gamma parameter is that nowadays there's no experimental setup available to getting a measure, and the theoretical derivation for it was out of the scope of the thesis. So we propose to measure it from simulations to obtain a result for the work. Basically, you can see that you can obtain the mean value from your simulations and infer the value of gamma with the deviation from 1. So we run the simulations, putting the angular boundaries at different positions in the hydrolysis and synthesis direction, and we obtain a mean value for this gamma. Now, once that is done, you can go back to your equation, solve for the external work, and the equation gives you, if you are able to know this gamma parameter, a result that is compatible within its error bars with the true value, which is the one we put in the simulations for this external agent. However, as I said, you don't have actually a way to obtain this gamma parameter. So at the end, the only thing that is giving to you the integral fluctuation theorem is a lower bound. But again, has a relative deviation below the 5%. And I want to say here that experimental setups right now have like an error of 10% approximately for this type of scales. So actually our proposal for inference is more accurate than what you can do now in an experiment. But as I said, you cannot know gamma. At the end, you have just an approximation. Why don't approximate it from the very beginning, everything, and make your life simpler without having to rely on knowing this gamma parameter? You can obtain this if you let the system to work only in the stationary state. In that case, the integral fluctuation theorem can be simplified to this expression in which you don't care about that gamma, and you can obtain again, using the same steps, a closed equation to infer the external work. Now, in this case, however, since you don't know the initial state of the system, you have to approximate which is the entropy production at the stopping condition. But you always know that if you're going to wait the system to fulfill NH rotation in one direction or in the other, this entropy production must have a term, which is that number of times the entropy produced in a cycle in each direction. And the important point here is that at the end, the term that you're neglecting is only a transient term. So if you impose in your simulations or in your experimental measurements large enough NH or NS, you can make that this approximation is actually legit. So this is a way of obtaining another approximate result, but in this case, with, let's say, a way of controlling the source of error you're introducing. And surprisingly, with this approximate proposal, we could obtain results with a relative deviation below the 0.5% with the true value we introduced. Then again, as I said, depend only on putting the motor to rotate and counting the number of how much rotation you do in each of the directions. Something that has been measured in the 90s, so 30 years ago. These are the results for one of the theoretical results I commented to you. I also focused on the stream statistics of entropy production. Again, I don't have much time to show the details. You can ask at the end, but you can relate the results to bound the entropy production to bound other energy fluxes, just as work or heat. And in our case, we're interested in bounding, which is the output mechanical work that, as I said at the beginning, in general, a molecular motor performs. One can obtain equations for upper and lower thresholds that are just surpassed with a fixed probability alpha. However, these first closed equations, as you can imagine, are not super useful for our results because you need to fully characterize all the moments of the distribution of the exponential minus the entropy production. If such information was available, you will not need of asking about any inference nor anything. But if one sees at the asymptotic values, and in particular to the lower asymptotic bound, one can check that you have a theoretical expression that is much easier to access in our experiment. And is the one in which we based our results. Basically, this result depends on the temperature of the system. This is the temperature of the dissolution in which you put in your motor. You can know it easily. The macroscopic efficiency, this is the relation between the input chemical work you put into the system and the output mechanical work it does against external force. This parameter we want to infer. And it is important to notice that at the end, how much work you have exerted, how much work the motor has exerted against an external environment depends only on the number of transitions you do against or along with that external force. So you can use this equation to find a close one to infer the parameter we were interested in. Now, this delta mu was measured in experiments. I give the results in the master thesis. The only thing you have to worry about now is obtaining pairs of values of minimum of these differences of hydrolysis synthesis transitions and the probability of obtaining an infimum value, which is that or below or lower. And for that, what you can do is simply sampling some trajectories. This is leaving the system to rotate some time and recording for each trajectory, which is the minimum value of this difference you have achieved. Then you construct a histogram, and this probability for that bound you have measured of being surpassed or not is simply the cumulative probability of all the bins that are below them, because you're assuming the probability of obtaining a mean value, a minimum value, which is that you are interested in, or lower. And doing that, we can construct again the histogram for the minima, and obtaining for each of these values the corresponding inference. The best one we obtained was the one for difference between the hydrolysis and synthesis steps of -4, which was an influence of around 16.6, which is worse than the one we proposed at the end with this approximated proposal in the stationary state. But again, a relative deviation around 2%, much better than what you can do in an experiment right now. So just to summarize, we propose to obtain the potential the bias that the potential external agent was including in the rotation of the system. And for that, we went to recent theoretical results in stochastic thermodynamics, one that included the mean value over the stochastic relationship of the experiment. This is a mean value at the stopping times that with a very simple proposal at the end could give us results with relative deviations below the 0.5%. And we also looked at the extreme statistics of entropy production that could also give us very satisfactory results with a relative deviation just around the 2%. So both the integral fluctuation theorem at the stopping times and the extreme statistics of entropy production are suitable results to substantiate thermodynamic inference strategies. And that are, in fact, easy to implement in an experiment because at the end, the only thing that you have to do is, again, as it was done in the 90s, recording how much steps you do in each direction. Nothing else. You need a video of the motor. And I want to conclude this presentation by saying that even though I have presented a very particular case in which you want to infer an external agent in the particular molecular motor, these couple of techniques, you can apply all of them to any possible molecular motor in which you can put a description of a discrete model. And in particular, I want to mention this one, which is proposed for the vesicle transport in the kinesin, in which you have, as in the F1-ATPase and in the all others, some hidden transitions that are internal conformational changes of the motor you're not able to see, but you have always a pair of transitions that you can see because they rely only on the movement of the motor, what can be recorded. So simply seeing, again, probabilities of going forward and going backward, seeing how soon you reach now a bound that is not placed at an angular position, but at a particular distance from the beginning, you can infer the different biases or whichever other parameter you can at the end put in these expressions I show you at the end. Now, this said, I finish the presentation in here. Thank you very much for listening.
Thank you for the presentation. Now, turn for questions. Maybe we have